Okay, so now I come to another topic. So, this much I just had to talk about the stochastic processes and their measurability issues and their equivalence in various different notions. Now, we recall what do we mean by conditional expectation. Okay. So, these are basically recollections because I have assumed that expertise of measure theory and basic probability theory. So, let omega f p be a probability space and x a random variable on it with expectation of mod x finite, and assume that script g is a subsigma algebra of f. Okay. Then we write down this manner expectation E of x given g. Okay, we read it the following manner: conditional expectation of x given g. Okay. So, this conditional expression x given g is nothing but a random variable, but g measurable function. Okay, g measurable function such that for every a in g we have this condition to be true. Okay. So, that is the definition of expression x given g. What is that condition? That expectation of condition expectation of x given g multiplied with indicator function of a, that is equal to expectation of x multiplied with indicator function of a. So, here expectation is integration, correct. So, left hand side we are integrating expectation x given g on the domain A with respect to probability measure p, and right hand side we are integrating x with respect to the probability measure p on the domain A. Okay. However, on the left and right side both sides, so here on the left hand side, since this is g measurable function and a is also g measurable. So, left hand side this integration we can very well take as with respect to probability measure p, which is restricted to the sigma algebra g. Okay, I can take that. Okay. Okay, so that is the definition. Let us try to understand the definition in little greater details. So, we define another sign measure, basically this is not a measure. So, px is a single object, okay, which if we evaluate on a set A, where A is a g measurable set. So, that evaluation, that definition is the expectation of x times 1 indicator function of A. So, here this value could be positive or negative. However, this value, okay, so if we take the positive part of the inside, so that would have the finite value. If I take the negative part of this function and take expression, that would also have finite value. Why is it so? Because x has finite expectation, mod x is finite expectation. So, you would get a sign measure here. So, px is a sign measure, okay, for all a in g. Then what we do is that we also define p restricted on g, as I was indicating earlier, which is nothing but p probability of a, but a is in g. Okay. So, this is just a restriction of probability measure, not on the full sigma algebra f, but a sub sigma algebra g. Okay. So, this is also a measure. Now, this px measure and p restricted on g. So, this has a relation. So, what is that relation? That if any set A has measure 0 with respect to this measure, then that set has also 0 value with respect to, actually I should have written mod here, with respect to the total variation of px measure. Okay. So, what does it mean? That px is a sign measure. Every sign measure due to the Hahn decomposition has two parts, the positive part and negative part, and if you add those things, you are going to get the total variation of the sign measure, and the total variation measure is absolutely continuous with respect to this measure. Okay. I mean, why is it so? Because if any set A has 0 measure with this PG measure, then over that set this part would be 0 almost surely. So, expect this part would be 0. Okay. So, it is as easy as that. Okay. So, Px is absolutely continuous with respect to Pg, then we can use Radon-Nikodym theorem. So, Radon-Nikodym theorem says that we can find out a Radon-Nikodym derivative of Px with respect to Pg. Okay. And what is that? That would be exactly this. Why? Because this is written in that manner. Okay. It is written exactly in that manner, that this part is integrated on the domain A over with respect to the probability measure, and here this Px appears here. So, this expression x given g is the random derivative of Px with respect to Pg. Okay. So, this is another way of viewing a conditional expectation as a random Nicotin derivative. To define this way, we do not need to assume that the random variable has any finite variance, we just need it has finite expectation. Okay. But there are some other ways. So, if in addition to this you know that random variable has finite variance, then there is another geometrical way to define conditional expectation as projection. Okay. Now, we introduce few more notations. So, we write on expectation of x given b. B is just a measurable set with respect to f. So, that we define as expectation of x given the sigma algebra generated by indicator function of b. Why do we do that? Because we have already introduced the meaning of expectation x given a sigma algebra. Okay. So, that we find out and evaluate that on omega, any omega which is in B. Okay, does not matter what omega you choose. Why? Because this thing is a function, this conditional expectation, which is measurable with respect to the 1b, okay, sigma generated by 1b. Okay. And as I have mentioned earlier, that if y is measurable with respect to sigma x, then y is constant where x is constant, those parts. So, since 1b is constant on b, so this whole thing should be constant on b. Okay. Okay, so this is meaningful, the right hand side is meaningful. Whatever the value is, we are going to call that as expression x given b. Now, what do we mean by probability a given b? So, we are defining in this manner, in the following manner, expectation of indicator function of a, that is now a random variable, because a is an event, indicator function of a is a random variable, and given b. Okay. So, whatever we have defined earlier, using that we are defining these terms, which you have possibly seen earlier also in some earlier probability courses, and we need to just cross verify whether this definition is consistent with those definitions. Okay. Okay, so that we do in the next slide. So, we also get the Bayes theorem. So, what we want to show that probability a given b multiplied with probability b is equal to probability of a intersection b, correct. So, this is actually defining notion of probability of a given b, correct. So, we prove here that thing, okay, using the earlier definition. Okay. So, here probability a given b would be written using this notation. Now, here b is like sigma algebra generated by indicator function of b. So, we write down everything here explicitly. So, it is expectation of 1a given sigma of 1b evaluated b, and pb is retained. And then what we do is that we consider this is a value, and this is the measure on which this value is achieved. Okay. So, then we can think that this value is multiplied with the indicator function of b, and that is a function, and we are finding out area under the curve, like we are finding out the integration of that. If we do that, then exactly we are going to get the value and the measure where the value was achieved. So, we do that way. So, we write down everything, multiply 1b and take the expectation. Okay. There is a rationale behind getting this thing from here. One can actually cross verify the reverse direction. If you find out it, you are going to get this value multiplied with the probability of b. Okay. So, whatever the manner you justify. So, now after that what we do is that we use this fact that since this is measurable with respect to the sigma algebra written here, so we can put it inside. So, this is a property which I am also going to quote separately later. So, what we are going to get is the expectation of this 1b is now with 1a into 1b. So, this product appears here and the sigma algebra appears here. And then we notice that there are two expectations. So, this first expectation gives me a random variable which is sigma 1b measurable, but another expectation would give me just a real number. So what is that? Expectation of conditional expectation is the expectation of the random variable itself. So we are going to get expectation of 1a into 1b, but 1a into 1b is nothing but the product, the integrator function of the intersection of a and b. So expectation of integrator function is probability of the set. So we are going to get probability of a intersection b. Okay. For the same manner, exactly, because a and b we have not specified any particular thing. For symmetry, we are going to get we can replace a by b and b by a. So we are going to get pb given a, product p of a is equal to p of a intersection b. So we are going to get that p of a given b into pb is equal to p of b given a into p. Okay, because a intersection b is same as b intersection a. Okay, next we say what do we mean by independent events. Okay, so the definition is that if a and b are such that probability of a intersection b is product of probabilities p of a into p of b, then we say a and b are independent. Okay, so probability of intersection is product of probabilities. Now we define what do we mean by independent sigma algebras. So let f and g be two subsigma algebras. Okay, so two sigma algebras on a non-empty set omega, such that for any a from f and any b from g, the events, okay, a and b are independent. So it does not matter what a I choose or what b I choose from f and g, but all the time this pair I am going to get independent. Okay, so then we call these f and g are independent sigma algebras. Okay, so for example, if I take the trivial sigma algebra, we call trivial sigma algebra this, correct? So like empty set and the full set. So this sigma algebra is independent of any other sigma algebras. Okay, any other sigma algebra. So it is actually independent of this sigma algebra itself also. Now that would help us to define what do we mean by two independent random variables. Okay, x and y are independent if the sigma algebra generated by x and sigma algebra generated by y, these two are independent sigma algebras. Okay, so that is how we introduce independence of random variables. Okay, so here we consider this example to illustrate that independence, etc. So what we do is that, so let so it is a very concrete example. We take omega as closed interval 0 1, b is the sigma algebra on 0 1, m is the Lebesgue measure. Okay, and then Lebesgue measure of closed 0 1 is 1. So this triplet is a probability space. So now a set x is equal to indicator function of 0 to half. So this is the same example time and again. Okay, so coming from closed 0 1 to r. Okay, so this indicator function we consider. Now we construct another random variable y on the same probability space such that x and y have same distribution, but x and y are independent random variables. Because generally when you say that, okay, give me an example of two different random variables, two independent random variables, the straightforward answer is that, okay, let us consider outcomes of two independent random experiments, tossing coins twice. Okay, first time outcome would be x, second time would be y, so they are independent. However, we are not considering the definition of random variable as an outcome of random experiment, but a measurable function. So it is important to produce example of independence, okay, in this setting. Okay, so let us see what we do. We take y as indicator function of 0 to 1/4 and add with indicator function of half to 3/4. Okay, so what we do is that total measure where y is 1 is still half, because for 1/4 length it is 1, and again here for 1/4 length it is 1. Okay, So the y thus constructed is surely a Bernoulli random variable having values 0 and 1 with half and half probabilities. However, if we, so this line I just explained, okay, so they have the same distributions, they are identically distributed. However, if we consider the joint distribution, probability x is equal to I and y is equal to j, that turns out to be 1/4 all the time. Whatever I, j you choose, I is equal to 0 or 1, j is equal to 0 or 1, all the time left hand side is 1/4. And right hand side is also half into half, 1/4. The way it is constructed. So here this is a construction of a pair of independent random variables. Okay, so if you can define two independent random variables this way, you can actually define a countable collection of independent random variables this way. Okay, in the similar manner. Okay, so next we introduce another term, distribution measure of a random variable or law. Okay, what do we mean by that? So we were talking mostly about the domain of x, correct, the omega, okay, the measurability, etc. Now here when we do not have that modeling setting, Kolmogor's model setting, but we just consider random variable as outcome of random experiment, then we don't see that omega, we just see the realization of the random variable. And then we ask that, okay, how often the random variable took that particular value. So that also gives you a measure, correct? So this measure is the distribution or law. Okay, so let us write down this, let us clarify what do we mean in this language. So let x be a real value random variable defined on omega fp, this probability space. Then the law px is a measure on the measurable space RBR, that is the range space, okay, such that the px of a is the probability of getting all those omegas as the x omega is inside A, okay, is in A. So if px satisfies this for all A in BR, then we call p subscript x as the law of x, okay, or the distribution of x. So let us look at the example, one example. Okay, so this is also the same example what I have shown earlier for construction of a random variable having normal distribution. So here we are recollecting that random variable. So we have there the measures, the probability space as very standard choice, the unit interval, Borel sigma algebra on that, and Lebesgue measure, and x is the inverse of the CDF. Here CDF is a monotonic function, so it is continuous monotonic function, so there is no problem. It is the inverse exists, and it is given by fx is equal to minus into x 1 over square root 2 pi e to the minus t square by 2 dt. So then what would be px for this case? So px of a is here integration of this integrand over a. So that is the px for this case. Okay, so let us revisit some properties of conditional expectation and conditional probability. So some of this property I have actually used earlier, but I have never specified those explicitly. So here I'm doing that. So let x be a random variable defined on the probability space omega fp with finite expectation. Finite is important because that is the underlying thing we are doing, okay, to define conditional expectation. Then conditional expectation of x given g for, it's not defining criteria, I'm just saying that, okay, for these special cases it has very nice expression that, okay, when g is sigma algebra generated by x or superset of that, super sigma algebra of that, for those cases this conditional expectation of x given g is exactly x. Okay, on the other hand, if g is independent of sigma algebra generated by x, then expectation of x given g is just expectation of x. So this also coincides with the basic intuition that the sigma algebra given here is representing the information. So what is that? So if your sigma algebra is equal or more than the sigma generated by x, that means it has all the information of x, then given all the information of x, and I'm asking what is the averaging. So you are not averaging at all because you have the information already. So you get the x itself. On the other hand, if g is independent of sigma x, that means g has no information of x. Okay, and then you are trying to find out the expression of x given this information, but that information is not helping you anyway. So then you are going to just get expectation of x. Okay. Say for example, if you choose G to be trivial sigma algebra, which is of course independent of sigma x, then also you are going to get expectation of x. That is a special case. Okay, so these are actually one can actually prove step by step, but for the sake of our purpose of the course, we are not going to visit the proofs. We are just recollecting these facts which we are going to use in the course later. Okay, so this is the second property which I have used earlier in the proof of conditional probabilities. So here, expectation of product of x and y given g, okay, it becomes x into expectation of y given g if x is g measurable. Okay, if x is g measurable, then you can take x outside of this expectation. Okay, so this thing actually you can see here is a manifestation of this property also, because if you prove this part is trivial. Why? Because if g is sigma x, so then x is g measurable, so you can take x outside of expectation, then inside only 1 remains. So expectation of function expression 1 is 1 always, so it would be x. So if one proves this, then this is trivial. Okay, a few more properties. Okay, so let G1 and G2 are subsigma algebras of F. Okay, and X is a random variable on the probability space omega Fp. If X is conditionally independent to G1 given G2, what does it mean? That X belongs to A, is that event, and a member of G1. So if I take probability of intersection of these two given G2, then that joint probability of conditional probability of the joint event is product of the conditional probabilities. The probability of x belongs to A given G2 multiplied with probability of that event from G1 given G2. Okay, so if that is the case, then one would get expectation, conditional expectation of x given here you have G1 and G2 together. Okay, so what do I have? I have just x and G1 are independent, and we know that okay, x and G1 are independent given G2, and then we are asking that what is the conditional expectation of x given sigma algebra generated by G1 and G2 together. So that turns out to be expectation of x given G2. Okay, so here as if that okay, since x is independent with respect to G1, so you can ignore G1. Okay, as if that thing happens here. However, if you have x and z are independent, okay, x and z are independent, but you do not say that okay, whether they are conditionally independent with respect to y, you do not put that condition. So then you do not get, it does not imply that expression is given y comma z is equal to expectation of x given y. It does not imply this. Okay, so you need that independence, the conditional independence. Okay, you need conditional independence, then only you can assure this. Okay, so now we see what is the implication of conditional expectation of x given a sigma algebra G. So this implication is useful when x has finite variance. So we consider here, say y is a random variable which is g measurable, okay, any arbitrary, okay, and then we consider this the product of the expectation. The product is taken the following manner. we take conditional expectation of x given g and we subtract conditional expectation of x given g from x. Okay, so we get a random variable there, and again we consider conditional expectation of x given g and minus y. So here y is g measurable, conditional expectation of x given g is also g measurable, so their subtraction is also g measurable. So this random variable is in the subspace of g measurable functions. Okay, and then if we take expectation of this product, okay, which is nothing but inner product in the L2 space. Okay, so this turns out to be 0. Okay, I am not proving this, but I am just quoting this result. This is 0, and also I am highlighting the implication of this fact. So conditional expectation of this product is 0. Okay, so if x is finite variance, then the conditional expectation of x given g, okay, this now can be considered as projection of x in the subspace of variables measurable to g. Okay, so let us explain this with this drawing. Consider that whole this plane is the L2 space of random variables which has finite variance, and imagine this line is corresponding to the subspace of g measurable random variables. So g measurable L2 random variables, and then consider y is one such random variable, and here expectation of x given g is on this subspace, expectation x given g is on this subspace. We consider this is the point. Okay, this point corresponds to expectation x given g. Then difference x minus expectation x given g is this part, and expectation x given g minus y is this part, and this equality says that the expectation of this product is 0, or saying that the inner product of this is 0, that means they are orthogonal. Okay, so inner product of this is 0, that means they are orthogonal. That means that this is projection of x on this subspace of g measurable L2 random variables. Okay, so by this I stop now. Thank you.